All right, so let's talk about the capacitor in the S domain. Actually, let me talk about one really quick thing. I said we shouldn't worry about this right now because I had thought that the way you get between these two was just by the math, which it does work. I did it by just solving for IL of S here, but really what they're doing here is this VL expression converts directly to this VL expression in the S domain, and this IL expression converts directly to this IL expression in the S domain. So you can also see that. Right, this is VL. By time integration, you divide by S, so that's why I get VL over S here. The constant comes along for the ride, and then my initial condition is a constant, so that just gets divided by S, and so you can see how that maps. And so that's the same thing that's happening with the capacitor here, right? This equation for IC maps directly to this expression for IC in the S domain, right? Time differentiation. Again, we are saying IC of T is equal to C dvc of t dt. Time differentiation says, let me just put the little Laplace thing here. Time differentiation says my constant comes along for the ride. If I'm doing a derivative, I multiply, so I go VCS here. And then I can subtract my initial condition, which is going to be VC of 0 minus on my capacitor. And so then if I multiply through here, I get C or SC VC of S minus C VC of 0 minus, and that's going to be equal to IC of S, and that's exactly what I have here. And if you were to do the same for, either you can solve for VC in this expression and that'll give you this expression, or I can take this expression here and just directly Laplace transform it. So VC of 0 minus is a constant, we divide by S, that gives us the S domain. Or we do time integration, which means we have to divide by S, so we get IC of S divided by C, and then we have the 1 over S as well. So you can kind of see how this works. And again, we have two alternative versions here. We have a version where we write things in terms of the voltage across the capacitor, right? So each of these terms is a voltage, and so the initial condition gets mapped to a voltage source. Or we have this current expression where we model this as basically a capacitor in parallel with the current source, and the initial condition gets plotted or mapped to a current source, okay? So that is how you transform resistors, inductors, and capacitors into their S-domain equivalents. Take note of the fact that if the initial condition is 0, right, the voltage here is 0. So again, it's just a capacitor at that point. It's just 1 over SC. And the initial condition just completely goes away from the expression, and you just end up with Ohm's law here, right? The voltage is equal to the current divided by the impedance. The initial condition is one of the main distinguishing factors between what we've already done and what we have here. Okay, and the same goes for this expression here. So in this case, because the current source is in parallel, if we assume the initial condition on the capacitor is 0, the current in this branch is 0, and so all we get is a capacitor, which again just follows Ohm's law, right? I is going to be equal to V divided by this impedance, okay? So that's it. We're going to end this video here. And in the next video, I think I'll do a little bit of a wrap up on this. I kind of did it already, but I'll do it again. And then in the last couple of videos, we're going to solve a couple example problems using this this circuit modeling technique in the S domain, and then we will be completely done with this course. So I'm very excited to say that. It's been a long road. It's been a lot of material. And yeah, let's go ahead and wrap things up.